In magnetic resonance fingerprinting, the challenges of high undersampling and artifacts can be addressed by combining a deep image prior module with a Bloch consistency enforcing autoencoder. This approach, named Bloch autoencoder regularized deep image prior, or BARDIP, leverages the deep image prior's capability to act as an implicit image prior without requiring ground truth. By doing so, BARDIP achieves up to 30 times faster convergence compared to the current deep image prior-based baseline on simulated data, while maintaining equivalent or better accuracy in quantitative mapping. The BARDIP architecture consists of three main components. The first is a deep image prior module for deliasing input time spatial magnetization images, or TSMI. The second is a Bloch response module, which relates quantitative maps to TSMI voxelwise. The third is an autoencoder module, responsible for enforcing Bloch consistency. This innovative method has the potential to significantly improve the efficiency and accuracy of magnetic resonance fingerprinting-based quantitative imaging. By integrating the strengths of deep image priors and Bloch response modeling, BARDIP offers a promising solution for overcoming the limitations of traditional magnetic resonance fingerprinting approaches. Researchers have long been interested in understanding the dynamics of complex systems, particularly those exhibiting nonlinear behavior. In recent years, the use of machine learning algorithms has gained popularity in this domain. However, most existing methods rely on simplifying assumptions, such as linearity or Gaussianity, which may not accurately capture the underlying dynamics. This study proposes a novel approach, leveraging a class of models known as normalizing flows, to model and analyze complex systems. Normalizing flows are a type of generative model that can capture nonlinear relationships and high-dimensional distributions. The authors employ a specific type of normalizing flow, called the neural spline flow, which is well suited for modeling systems with multiple interacting components. The authors demonstrate the efficacy of their approach by applying it to a series of complex systems, including the Lorentz attractor, a classic example of a chaotic system, and a real-world climate model. They show that their method is able to accurately capture the underlying dynamics of these systems, outperforming traditional methods in terms of predictive accuracy. A key advantage of the normalizing flow approach is its ability to handle high-dimensional data and nonlinear relationships, making it particularly well suited for modeling complex systems. The authors also highlight the interpretability of their method, which allows for the identification of key drivers and interactions within the system. While the study demonstrates the promise of normalizing flows in modeling complex systems, the authors acknowledge several limitations, including the need for further research into the scalability of their approach and the potential for overfitting. Future work will focus on addressing these limitations and exploring the application of normalizing flows to a broader range of complex systems. The proposed BARDIP approach is evaluated and compared to the baseline DIP-MRF method, showcasing its superior performance in reconstructing quantitative maps from undersampled magnetic resonance imaging (MRI) data. Figure 2 illustrates the reconstruction errors, measured as mean absolute percentage error (MAPE), for T1 and T2 maps, versus iterations for both approaches on simulated data with signal-to-noise ratios, SNR, of 40 and 35. The results demonstrate that BARDIP achieves a more rapid and steady decrease in MAPE during the entire course of training, reaching an acceptable error level within 1,000 iterations and plateauing after 10,000 iterations. Table 1 reports the performance metrics, including MAPE for T1 and T2 maps, and peak signal-to-noise ratios, PSNRs, for PD, averaged across 17 slices of simulated brain maps at 1,000 and 30,000 iterations. The superior performance of BARDIP is evident, with the best overall metrics highlighted in bold. The advantages of BARDIP over DIP-MRF are attributed to its ability to reach an acceptable error level within a shorter number of iterations, without the need for early stopping to prevent overfitting. This is credited to the pre-training of the BDAE module on the available MRF dictionary and the choice of x0, which corresponds to the scaled-back projection defined in equation 2. The additional regularization utilized by BARDIP, through its Bloch consistency enforcing coupled loss, is also responsible for its improved performance. Figure 3 showcases the reconstructed quantitative maps for a real scan slice, demonstrating the qualitative improvement of BAR-DIP over DIP-MRF. The results highlight the potential of BAR-DIP to accurately reconstruct quantitative maps from undersampled MRI data, with implications for improved diagnostic capabilities and patient outcomes. Magnetic resonance imaging, MRI, data reconstruction using deep learning methods has shown promise in shortening acquisition times and improving image quality. Tissue maps generated by different techniques, including positron emission tomography, PET, image reconstruction and dynamic MRI, demonstrate the versatility of these approaches. Convolutional networks, such as the U-Net, have been successfully applied to biomedical image segmentation, leveraging their ability to learn complex patterns in imaging data. Additionally, compressed sensing and extended phase graphs have been utilized for MRI reconstruction, further expanding the toolkit for image acquisition. Fast imaging techniques, such as fast imaging with steady-state precession, FISP, with spiral readout, are crucial for efficient data acquisition. These methods have been evaluated through various studies and publications, highlighting significant advancements in MRI reconstruction technology. The use of deep learning methods has been shown to improve image quality while reducing acquisition times, enabling the development of novel MRI protocols. Furthermore, the integration of compressed sensing and extended phase graphs has the potential to enhance the reconstruction process. The presented approaches have been validated through numerous studies, demonstrating their efficacy in MRI data reconstruction. As the field continues to evolve, further research is needed to fully explore the capabilities of deep learning methods in MRI reconstruction and to address the existing limitations of these techniques.